In this video, we're going to be working through practice problems for the second or test 2 in AP Pre-Cal. And as always, I'm just going to throw out the disclaimer that this is a selection of problems from AP Classroom. It applies to our current unit, but the best way to study for the test is going to be to go back and look at those quizzes, analyze your errors, and then go back and work similar problems on the other form of the quizzes, the homeworks, and the notes book. So the first one's a really typical question for what we've been doing lately. Like, here's a picture of the graph, write an equation that could be it. Okay, so, and all the answer choices are factored. And I'm intentionally not showing them here so that, we can build up our answer and then find it in the answer choices rather than going from the answer choices. So what I'm seeing is a polynomial that's got a double root at least, but an even multiplicity root at x equals -3, and another one at x equals 2. So I would think, maybe like x plus 3 for the x equaling -3 squared and x minus 2 squared. Okay, that's kind of my hypothesis, and I'm going to check against the answer choices. All right, -3 plus 2, we're not going to choose that. We're looking for 1. Okay, 2 double roots. Oh, okay, that's a good question. All right, so it's 2 double roots. X equals -3 would make x plus 3 equal to 0, so that's its factor. And, all right, so it's D, and we'll move on. Next one says, which of the following describes the behavior of P as the input values decrease without bound? This one, this whole problem set is going to be tough for me to get on the screen at once. The problems are really, really wide. I'm realizing that now, and I know how I can fix that, and I will make sure that I do that for the next one. So, as the input values decrease without bound, I'm having trouble even. Sound like it's on the far right edge. Let's see if I can drag this over. Yeah, that's kind of working. All right, so when they say input values decrease without bound, what we're really saying is x is approaching -infinity. Okay? And so that should, in your head think, okay, we're talking about taking a limit as x approaches -infinity. And we've got an equation for p, so yeah, there we go. And all right, so we want the limit as x approaches -infinity of p of x. Okay, now that's going to depend on the degree and leading coefficient of p. We're going to find that looking at the highest power term, that's x to the third, so that's an odd degree. And a positive leading coefficient. Okay, since it's just x to the third, that's coefficient 1. And so odd degree polynomial with positive leading coefficient, that's like y equals x cubed. Looks like that. Okay, so the limit as x approaches -infinity down here. Okay, it's going to -infinity. Okay, so the output values decrease without bound. Okay, yeah. I don't think we would have reason to believe the output values get closer to -4 quite yet. Because at this point, all of the end behaviors of our functions are either infinity or -infinity, right? All right, number 3 is talking about a polynomial given by a times x to the b, where a is an integer and b is a positive integer. Okay. It's known that the limit as x approaches -infinity of f is -infinity, and the limit of f as x approaches positive infinity is going to be -infinity. I think we should maybe draw a graph of that. So, all right, so f of x is approaching -infinity as x approaches -infinity, something like that. And then as x approaches positive infinity, f is still approaching -infinity. So, I mean, who knows what it's doing up there. I guess if it only has one term, it's actually probably not doing that. It's more like that. So it looks to me like we're going to know that we have an even degree and a negative leading coefficient. Because to me that looks like the graph of y equals -x squared. Okay, so the value of a must be positive. No, that's out. In fact, I'm going to not scratch it out there. I'm going to scratch it out right there because that's the issue. Value of a must be negative. Okay, true. Because as x increases without bound or decreases without bound, the end behaviors of f are different. No, they're the same. Right? So that's not true either. Value of b must be even. Yes, that's true. Because as x increases without bound or decreases without bound, the end behaviors of f are the same. Yeah, that one's true. And then D is the value of B must be odd. Well, we know that's not true. It's an even degree. All right, the next one is the function h is given by h of x equals negative x to the 4 plus x to the 3 plus 20x to the 2. Which of the following statements is true? All right, now this is talking about a global minimum, which is something that we do need to be aware of in this class, and I have mentioned it in classes, kind of just like thrown off to the side in one of the notes. The global minimum or the global maximum, it's the greatest of all of the local minima or maxima. Okay, and if we have an even degree polynomial, we must have some sort of global minimum, right? Maybe it's fourth degree, it kind of looks like that. Maybe it's a second degree with a negative leading coefficient. Looks like that. That's got an absolute maximum. Something like that. If that one's smooth, that could be a polynomial. And then absolute minimum would be here. There would be no absolute maximum because it just goes up forever on both sides. Now, always the question is, what if it goes down to the exact same level and then it still has an absolute minimum? It's just that both of these represent the absolute minimum because it achieved that minimum value 2 different times. All right, so then I'm going to factor this thing, okay? Because I guess we need to sketch a graph is what's going on. So I've got negative x to the 4 plus x to the 3 plus 20x to the 2. I'm going to factor out negative x to the 2 so that the leading coefficient is positive, so I'm a little bit better at factoring it. I'll be left with an x to the 2, a negative x, and a negative 20. Yes, and that's something I can factor. Okay, two numbers that multiply to negative 20 while adding to negative 1 would be negative 5 and positive 4. Okay. And so if I was to sketch the graph of this thing, have zeros at negative 4, 0, which is going to be a double root, and at 5. Okay. Now this is a fourth degree polynomial with a negative leading coefficient, so I know that the end behaviors are kind of like that last one we were looking at, like negative x squared. Okay, so I've got all of this, and I know it's going to pass through at negative 4 in a second. Squared times x minus 5 times x plus 4. Okay, it's going to pass through at negative 4 and at 5, but bounce at 0. Oh, I know what it's going to be. I just wasn't looking at the question answers closely. All right, because I'm saying, like, how do I know which of these goes higher, right? Like, I've got two different maxima. I've got one right there and one right there, and I don't have any information to say which of the following statements is true. Hold on. So I just took a second there and did a little searching on the internet because I'm realizing I didn't think you had enough tools to answer this question. I can confidently say there's going to be a global maximum between x equals negative 4 and x equals positive 5. I can say there's going to be a local maximum between negative 4 and 0, or I could say there's a local maximum between 0 and 5. But without doing calculus on this thing and actually checking, what the height is at those extreme values, which you don't know how to do, but I didn't really know how to do this. So I went into AP Classroom to look at the original personal progress check, and I'm just going to read you their commentary on this question. Correct answer choice is D. And maybe y'all just intuitively would know this. I'm not sure I necessarily knew this was true. I'm going to be thinking about this more later. It says answer D is correct. The function is of an even degree with a negative leading coefficient, which we had definitely ascertained. Therefore, the graph opens downward. Yes, factorization of h of x results in what we got. This reveals a 0 at negative 4, a 0 with multiplicity 2 at x equals 0, and a 0 at x equals 5. Therefore, the function has local maxima between negative 4 and 0 and between 0 and 5. The interval from 0 to 5 is of greater length than the interval from x equals negative 4 to 0. And the function therefore attains a greater maximum on the interval of greater length. Okay, so I'm not sure that I knew that a wider interval doesn't necessarily meant that it was going to go higher. That's evidently got to be the case because they would not have published that in AP Classroom if it was not. So now we know. Okay, wider interval gets you a higher maximum. Okay, learn something today. Okay, so the next one is a polynomial is factored and the domain is -5 to 5. Okay, so which of the following is true about the graph of P? And I'm not going to pull that in. Graph of P intersects the axis at 3 points. That's true. 3, 2, and -1. Has 4 local extrema. I don't think that's going to be possible. No global extrema. Maybe we should go ahead and give a sketch of this thing. So I'm just going to draw it right on top of the on top of this one, because I know that's not going to be true. Not going to be 4 local extrema on a third-degree polynomial. There's going to be at most 2. So I've got -1, 2, and 3. Okay, it's going to be a third-degree polynomial with a positive leading coefficient, so it's going to go up, and then down, and then up again. So it's going to have 1 local maximum, 1 local minimum. Okay, and intersects the x-axis at 3 points. That is true, but all 4 of those answer choices have that, so that's obviously going to be true. What else was I thinking about this graph? I thought there was something else I wanted to say about it. Oh, yeah, I could draw in a y-axis if I wanted to, but maybe about right there. And the y-coordinate would be whatever I got when I plugged in x equals 0, p of 0 equaling -3 times -2 times +1, which is 6. I'm just gonna throw that out there. So the other one's 2 local extrema that are also not global extrema and has 2 global extrema. Again, I don't know how you're supposed to determine. Maybe it's the fact that, again, this width of the interval, going to -5, it's going to go really far down. And, I might actually take out this graph and try to draw something a little bit more proportional. If it's going down to -5, it's really negative down there. And, oh, whoops, that's still going to be my y-intercept. And then, maybe down and then up like that. So I think it's reasonable to assume that, and it's probably not an arrow like that. It's going to eventually end at 5, which I'm just going to say is right there. Okay, I'd say if I had to take a bet, I'd say that the global extrema are going to happen at the endpoints. And so 2 local extrema that are also, okay, but it's going to have global extrema because it's a polynomial in a closed interval. And I'm not sure if that's a fact I was supposed to tell you, but it's true. Any polynomial in a closed interval will have a global maximum and a global minimum. This might be the type of thing we come back through and clean up on, in March and April when we start reviewing for the AP exam. Obviously, there's not going to be any global extrema talk on this upcoming test. I'm just kind of getting all of the polynomial discussion I can out of this problem. And so, yeah, it does have 2 global extrema. I'm going to go ahead and say that the local extrema are not global extrema, but again, I'm going to go look up the rationale in AP Classroom. Yeah, I gotta express doubt about this one. This one clearly says calculator not allowed, and then it just presents as fact that the global extrema happen at the endpoints, just like obviously. And to me, that's not obvious at all. It just says there exists 1 local extremum. It's at least 1 local extremum, I guess exactly 1 in this case, between each 2 distinct real zeros of this function. The endpoints of the restricted domain are the locations for the global extrema. No justification for that. I'm not sure how you're supposed to know that with certainty. So, yeah, I think we're going to just disregard that one too. All right, polynomial function, here we're back to it. Okay, x squared plus ax plus 9, where a is an integer. For p, that's the polynomial, which the following statement is true about the multiplicity of the 0 at x equals 3. It's multiplicity 7. Yes, that's answer choice A. We can read the other ones. Oh, I guess I didn't consider that. We could have. Yeah, we could have A equaling -6. And then we would have, actually, it could be, it could be up to even 9. Let me think about this. Okay, yeah, so let's just read the answer choices. X equals 3 is a 0 of x squared plus 9. That is not true. Okay, if I plug in 3 to x squared plus 9, I'm going to get 18. So that's not going to work. Multiplicity could be 9 because of the original factor being 7, and then x squared minus 6x plus 9. That's what I was saying. Yeah, that breaks up into x minus 3 times x minus 3. So if that did happen, this would just be 2 more copies of x minus 3, and I'd have 9 total copies. Okay, so it's going to be this one. If it was x plus 3, then, I couldn't go with x minus 3s, the 7 of them. Right, so that was a good one, and a good example of why, you got to read through all the answer choices. The number one, or A looked really appealing, but it was that must. Okay, that's not necessarily true. So which of the following functions has in behavior that and that also? Okay, so as x approaches infinity and negative infinity, p of x is approaching infinity. So we're going up on both sides. So we're looking for an even degree with a positive leading coefficient. So, well, I like the way this one works. Okay, B is going to be suitable. A has degree 3. C has a negative leading coefficient because of that 10 minus x. And also it's degree 3, so that's really not going to work. And then D is 4th degree, so that would be good, even degree, but it does also have that negative leading coefficient because of the 10 minus x. I like that one a lot. I kind of wish that I had seen that one and put it on the regular version of the test. Here we have another one, and this is the one thing that gives me pause for telling people to just kind of disregard the binomial theorem and be like, just multiply it out. Because I don't really think you're going to want to take h plus t to the 7. Now, I know the type of score we're shooting for on the AP exam to get a 3, 4, and 5. And it's none of those are, one multiple choice question is not going to kill any of us, keep us from achieving our goals. But I wanted you to be able to solve the problem. So this one we are going to need to use the binomial theorem. We're going to need to use Pascal triangle because we're going to do the expansion of, but I guess I need to read the question a little more closely. We're going to flip a balanced coin 6 times. So they do the expansion h plus t to the n. That's going to be h plus t to the 6. So I need the triangle up to 6. Okay, so that's going to be 1, 5, 10, 10, 5, 1. And then 1, 6, 15, 20, 15, 6, 1. All right, so exactly 2 heads and 4 tails. Okay, you can even see the left edge. Triangle, there we go. So if I was going to set up to multiply h plus t to the 6, what I would do is I would kind of copy down 1, 6, 15, 20, 15, 6, 1. And then I would do, power of h and power of t. And so it would be, h to the 5, or pardon me, h to the 6, t to the 0. And then it would descend down to, h to the 0, and t would start at t to the 0 and go up to t to the 6. I'm interested in 2 heads and 4 tails. So that's going to happen, right here. And it doesn't matter if you start h at power 0 and go up as you go down, and then start t at 6 and go down. It really doesn't matter, right? You're going to get the same thing because of the symmetry of the triangle. So that's going to be h to the 2 and t to the 4. So it's going to be 15 h to the 2 t to the 4, and that's b. Okay, so that's pretty easy if you do the triangle. But if you don't, then that could be a long endeavor to take h plus t to the 6. But I think that this question is already kind of challenging on the level that you'd have to know that you need to take h plus t to the 6 and then look for h to the 2 t to the 4. I'm not sure that the wording of this question, they give you the example, but it still would be tough. So, this one's a hard one. On the upcoming test with the binomial theorem, you just feel free to multiply it out if you want. There's nothing to the 7th power. So the function f is a quartic polynomial with this form. A is a real number, and each of the ri's are integers. It is known that the x-intercepts of f are -1, 0, and 2, 0. Okay, so we've got root 1, root 2, root 3, and root 4. And so, we could just say that with no loss of generality, f has 2 real zeros, each with multiplicity 2, so that's both of the ones I see. Both of these are double roots. So I know it's going to be x minus -1 squared times x minus 2 squared. Okay. There is sufficient information to define f. We've got a y-intercept, so we could say, times a equals y, and then we could use 0 and 24 to actually figure that out. And I might actually do that, just to remind you of how we do that, because that is something you might need to do on the test. Negative 2 squared. So that's 24 equaling a times 4, so a is going to need to be 6. So yeah, I've got f of x pinned in. Because the x-intercepts and the multiplicity of the zeros can be used to determine the Ri values, and the y-intercept can be used to find a. Yes, that's true. What's wrong with the other ones? There is sufficient information. Okay, these insufficient, I've got an equation for it. Because the y-intercept value 24 can be factored into the product of at least 4 integers involving the x-intercepts and the multiplicity of the zeros is known? What? Oh, whoops, looks like I was maybe just rolling. I looked on AP Classroom, and who knows, maybe I hope I wasn't working with video pause. I'll have to check on that. But I don't see this question in there, and I don't really see what is wrong with B, but I know that A is true. And I feel better about A. B is a little confusing, the wording, but the x-intercepts and the multiplicity of the zeros can be used to determine the Ri values, and the y-intercept can be used to find A. That is true. I'm just going to move on. All right, the next one, we talked about this one in my classes. I don't just love this one either. This one might be a little bit better for when we do modeling in the second semester, but I'm just going to take it back and do a little pre-explanation here. Hopefully in Algebra 1 and Geometry, they told you that if you've got 2 points, that there's only one line that goes through those 2 points. Yeah, just like that. And then maybe, hopefully last year in Algebra 2, it depends on your Algebra 2 class, and it's not the most important thing from Algebra 2, but it is one of the things that we're supposed to learn in Texas, and we definitely did it quite a bit in my class, is take 3 points and define a unique parabola from them. If the 3 points aren't on the same line, then there is only going to be one parabola that goes through them, and you can solve a system of 3 equations and 3 variables to figure out that parabola. We did it quite a bit in my class. We did it with and without technology. And so it stands to reason that if you had 4 points and they didn't all sit on the same line or parabola, then that would model a cubic function. So maybe, yeah, I don't think it's possible for a parabola to go through all 4 of those, right? Because I'm going to have an up, down, up. Right, and maybe it looks like that. That's my best possible sketch of that. Fourth degree polynomial that goes through those, or third degree polynomial that goes through those 4 points. All right, so first table of values gives the coordinates of 4 points in the xy plane. That's why I was talking about 4 points, and 3 and 2. Second table gives different function model types, like they ran a regression in the calculator and predicted a value at x equals 2.5 for a best fit function of that type. And notice this is going to be down here. This is a constant function. L of x is linear. Q of x is quadratic. That's not how you spell quadratic. And then C is cubic. So, I guess what I'm getting at is they labeled them like that. They gave you the equation to show you that it was the polynomial of these various degrees. It said the graph of one of the function models in the table passes through all 4 points. Okay, so there's only one that's going to be able to hit all 4, right? A parabola can't go through all 4 of those points. A line can't go through all those 4 of those points. A horizontal line, that's a constant function, that definitely can't go through all 4 of those points. In fact, it doesn't go through any of those points. And so as a result, I'm going to say that it has to be the cubic function that has all 4 points. And then it asks what's the predicted value at x equals 2.5 for this function. Okay, well, that's going to be the 9.125, because it's just like we need to use the cubic function. Got that. And now we've got some free response questions, and these are good. These are right at our level. So find all the values of x for which g of x equals 0. All right, well, g of x equals 0 when this thing equals 0. So that would happen when either 2x plus 3 was equal to the 0, or if x plus 2 is equal to 0, or maybe if x minus 1 was equal to 0. Okay. Then I'm going to solve each of these equations. I'm going to subtract 3 and divide by 2. I'm going to subtract 2, and I'm going to add 1. Okay, so those are my x values for which g of x equals 0. And then I'll do the same for h of x, and I'm going to set that equal to 0. But I'm going to need to do some factoring, so I'll do that down there. Looking for a greatest common factor. I see it. There's an x common to all 3 terms. So I have an x multiplied by x squared, positive 3x, and negative 4, and that's still equaling 0. And then I'm going to want to factor the thing in the parentheses. Think of 2 numbers that multiply to negative 4 while adding to positive 3. Okay, so it's going to be 4 and 1 somehow. So x maybe plus 4 multiplied by x minus 1. Whoops, that's going to be equal to 0. Okay, and then if these 3 things are multiplying together to equal 0, one of them has to be 0, so either x equals 0 or x plus 4 is equal to 0, which would happen when x was negative 4, or maybe x minus 1 equals 0, and that would be when x was equal to 1. Number 12 is giving us a function k, and it's asking us to find all values of x for which k of x is greater than 0. So this is solve an inequality with polynomials. So what we're going to do, we're going to get factored up, we're going to make a sign chart. You could probably make a sketch pretty easily of this thing. Oh, but we are going to need to be careful here. Let me think about this. Are there... Yes, all right, so 3 times negative 14 is negative 42. So I'm looking for 2 numbers that multiply to negative 42 while adding to negative 19. And I was thinking it wasn't possible because I don't know any factors of 42. Evidently 14 and 3, right? Figure that out. But also 21 and 2, but that could combine to make negative 19. So maybe if I had negative 21 and positive 2. So maybe I'll say k of x equals 3x squared minus 21x plus 2x minus 14. Okay, we're interested in where that's greater than 0. Okay, so we're going to continue to factor. So x minus 7 multiplied by 3x plus 2 is greater than 0. Now that I've got k of x factored, I need to make a sign chart. Because I probably need to find the zeros also. So I'm going to say, all right, maybe x is equal to 7. I can see that from the first factor. Or maybe 3x plus 2 equals 0. So I would subtract and then divide by 3. Okay, so both of these are single roots. I've got one at negative 2/3. And then another one at 7. Okay, and I'm going to choose x equals 0 as my test point. It's right there. Definitely not drawing a scale. Okay, so when I plug in x equals 0, k of 0 is going to equal 3 times 0 squared minus 19 times 0 minus 14. Okay, so the y-intercept of this function is negative 14. But what we care about is whether it's positive or negative, because we're trying to solve an inequality, not necessarily like draw a graph or anything. And then since both x equals 7 and x equals negative 2/3 are single roots, we'll see the sign of the function change at that 0. So I see negative and positive. So the intervals on which k is greater than 0, it's going to be through here and through there. Okay? It's going to be equal to 0 at the 2/3, whoops, and negative 2/3 and at 7, so we'll draw open circles there. But that's where x is greater than 7 and also where x is less than negative 2/3. Okay, and on this one, the parentheses do matter. Okay, I know I told some people that it's not important, and I think really what I meant was that on the increasing, decreasing type intervals, that's not important. But solving an inequality, although I know you're not going to have to do it on the AP exam on the free response, you're going to have to do it on the free response of, our in-class test. And, if you included 7 and negative 2/3, that wouldn't be totally true, because at x equals 7, k of x is not greater than 0, it's equal to 0. Okay, so just, be mindful of those endpoints, of those intervals when you're solving an inequality like we are in this unit. All right, m is a polynomial function of degree 4. Zeros of m include 0, 5, and 3 minus 2i. Write a possible expression for m of x. All right, so we'll say x minus 0. Okay, they didn't say anything about the leading coefficient, so maybe I can just assume it's 1. X minus 5, and then x minus 3 minus 2i is another root. Now it's a fourth degree polynomial, so there's got to be another factor. But if we've got one complex, non-real complex factor, we're going to have a second one, right? Because those complex zeros come in conjugate pairs. So it's going to be 3 plus 2i here. And we've got all 4 of these things multiplied together. That says possible expression for m of x. That looks more than possible to me. I don't think we necessarily need to, multiply these two things together so that we can get all real coefficients. I think factored form is going to be just fine. And I'm saying that's the last problem. That's going to be all for this review. That's all for this video. Thanks for watching.